Radiation therapy is one of the primary treatments for cancer. It's used as a treatment in more than half of all cancer patients due to its successful ability to kill cancer cells and shrink tumors. However, radiation also damages normal healthy tissue nearby. The mouth and gastrointestinal, or GI tract, are some of the main areas damaged by radiation therapy. We estimate that over 200,000 cancer patients in the US will develop GI toxicities every year from their radiation treatments. These toxicities will result in side effects such as nausea or diarrhea, to the more extreme of bleeding or narrowing of the GI tract, requiring hospitalization and expensive procedures. These effects can be severely debilitating and may cause patients to halt or stop treatment altogether, resulting in poor tumor control. To reduce these radiation-associated toxicities, we designed and created patient-specific radioprotectant devices that can selectively attenuate the radiation dose to normal tissue while maintaining the same anti-cancer efficacy. Specifically, we focused on available high-Z materials and determined the ideal materials that could serve as shields against radiation. In order to develop shields which fit the specific anatomy of patients, we used CT scans from patients to inform personalized designs. Using 3D printing, we created devices that could match the patient's anatomy and incorporated high-Z materials within the shielding device. We tested model shields in rats and in pigs. Using a single-dose radiation toxicity rat model, we found that the devices were able to protect healthy tissue in the mouth and rectum. The devices were tested in pigs and found to have good feasibility and reproducibility of placement in this larger animal model, which provides a better approximation of adult human anatomy. The devices were then modeled into patient treatments and found to reduce the dose of radiation by 30% to areas in the mouth, in head and neck cancer patients, and more than 15% in the GI tract of prostate cancer patients. The devices had no impact on the planned radiation dose to the tumor. From a safety perspective, we performed cytotoxicity studies and found no impact on cell viability with our shielding devices. In sum, we present new radioprotectant devices that may be used to reduce GI tissue injury in cancer patients undergoing therapeutic radiation. We are indebted to our sponsors for their support of this work, specifically the Prostate Cancer Foundation, Department of Defense, and the National Institutes of Health.